Hello there, my name is Felipe Eduardo da Silva. I am an undergraduate student of mechanical engineering from the Federal University of Technology in Paraná, Pato Branco. I'm here also representing the co-author of this work, Francisco Augusto Aparecido Gomes, and I will be talking a little about on the use of numerical approximate methods for predicting the heat transfer during the atmospheric re-entry of a blunt body. The main objective of this work is to analyze the aerodynamic heating in the stagnation point of a space vehicle re-entering the atmosphere. And to do this, there are two possible ways, which is using approximate methods or CFD simulations, which are also known as computational fluid dynamics. The problem behind CFD simulations is that they demand a long period of time to converge, and by using approximate methods, the results they come much more faster. But to implement these methods, we need to pass through some necessary steps. As shown here in Figure 1, we need to deal with the streamline conditions, which are the air properties before the normal shock that forms during a supersonic flight, and the shock conditions, which are the properties of the air after this normal shock. The first step in this numerical analysis that was created in Fortran is to input the trajectory of the space vehicle. In this work was considered the trajectory of the Brazilian microsatellite Sarah, as shown here in Figure 2. As we can see, Sarah starts its entrance in about 300 kilometers of altitude with a velocity close of 8,000 meters per second, and it reaches the maximum velocity at an altitude of 92 kilometers. The information provided by the trajectory is important because now we can implement the US Standard Atmosphere of 1976, which is an atmospheric model to obtain the properties of the air before that normal shock that I have shown in Figure 1, which are the streamline conditions. This process was described by Regan and Ananda Krishnan. After that, there are two ways of determining the properties after the normal shock. The first one is through the perfect gas model, and the second one is the thermodynamic equilibrium. The perfect gas model, it considers that the heat capacity ratio is 1.4, and the relations to obtain these properties are actually very simple, and they all depend on the properties before the normal shock and the Mach number, which is the relation between the streamline velocity and the speed of sound. The problem behind the perfect gas model is that it does not consider the dissociation and ionization of air components. And to do this, we need to start looking at thermodynamic equilibrium models, which consists of using tabulated data and polynomial correlations. These models, they consider that chemical reactions happen instantly, and over the year, one way of obtaining the air properties at high temperature suffered three great modifications. And in the last one, it is necessary to use 24 constants in this correlation to obtain the results. Here in the side figure 3 just showed this a representation of these models. There is a very similar representation in the book of John D. Anderson Jr., which is Hypersonic and High Temperature Gas Dynamics. The first properties are the streamline properties obtained by using the trajectory information in the US Standard Atmosphere, and the properties after the normal shock are the obtained through the perfect gas model and the thermodynamic equilibrium. So we have pressure, enthalpy, density, temperature, and velocity. Well, now that we have determined all those air properties, we can start looking at approximate methods. In this work was considered 5 approximate methods. I will not get too much into the details behind the implementation of all of them, but the 5 were Tauber-Manis and Edelman, Van Drijst, Sutton and Graves, Detra and Hidalgo, and Fey-Riedel. Fey-Riedel is also the only method that actually uses the properties that come directly from the thermodynamic equilibrium. Otherwise, in other methods, we have the perfect gas model acting for the properties after the normal shock. And if we create an integration, a numerical integration in the heat flux with respect to the trajectory time for all these methods, we end up obtaining the heat load. So, before we start talking about results, it is important to look at some conditions. This analysis was restricted to altitudes below 92 kilometers. The three wall temperatures were 1000, 2000, 3000 kelvins. Those are the temperatures of the surface of the space vehicle. And the increment of time used in the trapezoidal rule to obtain the heat load was 5 seconds. The first important result to guarantee in this work is the streamline conditions. Here in figure 4 is demonstrate a comparison between the streamline conditions obtained in the atmospheric model in this work and the US standard atmosphere of 1976. As we can see, the results were very close. Moving now to the heat flux results, we have in figure 7, 8, and 9 the plot of the heat flux in megawatts per meter square with respect to the trajectory time for the three wall temperatures of 1000, 2000, 3000 kelvins. As we can see, the behavior of all curves, they were very similar. The number 1, 2, and 3 in the results of Fay-Rideau stands for the model, the thermodynamic equilibrium model of 72, 74, and 87 respectively. The approach that always presented the highest results in all the three wall temperatures was Detrin Hidalgo, and the lowest one was Van Drijst. And another important thing to note is that even though three different thermodynamic equilibrium models were used in the Fay-Rideau approach, no big difference were found in the results. And as we can see, the method of Sutton grip is not presented in the wall temperatures of 2000, 3000 kelvins. This is because this approach is not recommended for wall temperatures above 1111 kelvins. The small fraction of time around 1750 seconds where the heat flux presented negative results is due to the fact that in that moment the environment ahead of the stagnation point is in a lower temperature. This way the heat flux will happen in the opposite direction. Coming to an end, we have this table where we placed the results for the heat load, which is just another perspective of the previously results, since this is an integration of the heat flux with respect to the trajectory time. As we can see here too, Detrin Hidalgo presented the highest values of heat load, and Fay-Rideau's approach, they were very close to each other for all the three wall temperatures. To conclude this presentation, we can say that there was a small difference between the results that came from the thermodynamic equilibrium model, since the approach using Fay-Rideau's method presented very similar results. And this makes a connection between this point and the the fastest way to get the results, because if you are in the first stage of a project and you just want to have an idea of the heat flux in this stagnation point, you can simply avoid using Fay-Rideau and the thermodynamic equilibrium model, because doing this you will not have to deal with a lot of values of constant in tabulated data and implement these correlations. And about the safest approximate method, we can say that if safety is the most important matter, we can look at Detrin Hidalgo's approach, because since we are dealing with the highest values of heat flux, inferior one will be automatically countered. And I say this in the way of developing a TPS, which is a thermal protection system for this space vehicle. This device will be responsible for the protection of the space vehicle. And another topic that was not taken into account in this work was the radiation effect. And the reason for this is that Sarah did not achieve great values of velocity where this effect will be important in the heat transfer. But to conclude, the heat transfer in the stagnation point is a combination between convective heat transfer and radiation heat transfer. I will be showing now the references used in this presentation very quickly, so if you want to see any of them, you can just pause the video and take a look. And that's it. Thank you for your attention.